Well, hello there. This is Craig Hain. I'm called Dr. Dell by my students sometimes, and I want to talk to you today about numbers. And this is really aimed at a discussion at people that are interested in teaching mathematics to students of all ages, really, but I'm thinking of high school students in particular. And I get asked a lot about what should we be teaching our students about numbers, and what, perhaps more importantly, should we not be teaching them? So there's really going to be two videos. This is going to be the first one. And this first videos, I'm going to talk about numbers for students that are not going to be mathematicians. These are people that are going to be interested in possibly in science or in engineering, and people that are not interested in going on into a professional subject, but are just interested in what I would call technical math. Now, I'm going to tell you some things that will probably be commonsensical and you'll agree with, and I may tell you some things that will be a little surprising to you. First of all, the obvious thing is all students, I believe, starting at a very early age, need to be taught about the counting numbers, 1, 2, 3, 4, and so on. And this is something, of course, that we all use, and virtually every educated person in the world needs to understand about these. Now, the main thing there is we have a decimal system, a decimal place system that we need to teach people about. And of course, you know all about that, but it really has to do with things that 352 is 3 times 100 plus 5 times 50 plus 2 times, well, I'm sorry, 5 times 10 plus 2. And of course, 10 is 100 squared. And so we have 10 digits, as you know, 1, 2, up through 9, and then we start over with a place system: 1, 1, 1, 2, 10, 1, 1, 0, 1, 1, 1, 2, and so on. And you know all about that. And the thing that we need to teach people, and I think in the counting numbers right off the bat, we should include 0. And the things we need to teach the kids then is the operations of addition and multiplication. That's the first thing. They have to learn their addition tables and their multiplication tables, as it were. And they have to understand the rules of these operations. Now, quite frankly, I think one of the very best way to teach students these things, even when they're very, very young, is to get them started using a power tool, which is the modern calculator. And there are a lot of things you can do with very young students, even as they begin to learn to count. You can even use this to help a student learn to count. You just teach them some basic things like 1 plus 1, and then what would that? Well, that's 2. And then what is it if you add another 1? Well, that's 3. What if you add another 1? Well, that's you're at 3, you add another 1, that's 4, and so on and so forth. And then once they begin to learn to add, you can let this instead of place cards like we used to use in the old days, you can use the calculator to create problems. What is 3 plus 5? And let the student guess at it, and of course then the calculator will tell them, bingo, the answer is 8. And then of course the same thing applies to multiplication. So I believe in, first of all, this is a power tool that is absolutely an indispensable, essential ingredient if you're going to do mathematics today. I don't mean this particular calculator. This happens to be a very good one that I use in the high school math. It's the Texas Instruments 30XA, and it costs about $10. But for a young kid, you will probably want to get them a smaller and less expensive calculator, one they can throw away or spill a Coke on or whatever. And you can buy good calculators today for $1. That's good for young children. Let them play with them and get them to playing games. Let them make up things to do. This calculator can almost be like magic to them. And if you get them playing games with this as a tool, that's not only going to be teaching them mathematics and the number system, but it's going to be teaching them how to do things. It's going to be teaching them process. And then you can ask questions where they can discover the answer with the calculator. And of course, I think it's good for all of us to be able to do addition and multiplication of basic numbers in our head, but there isn't any great advantage today to doing it with to learn complex algorithms that we don't need when we have the calculator available. And We can talk a lot more about that in the future if you want to, but in any event, I believe in using a calculator very early on and make sure that students understand the way the number system works in terms of place system and understands the basic rules of addition. And then they need to know things, and you don't need to use this terminology, but if you take two numbers and add them together, A plus B, that's the same as B plus A. Now, we know that's called the commutative law. It doesn't matter the order you do numbers in, that you add them in. Uh, you can add them in either order. First you add B and C, then add it to A, or you can add A and B and add C, get the same thing. It's called the associative law. They need to learn that if you add 0 to anything, you get the number back. If you multiply anything by 0, you get 0. Those are kind of the basic things. Now, you have similar rules for multiplication. I'll just put a dot up here. A times B equals B times A. And the same thing for the associative law. And of course now, the new rule down here you would get for with multiplication, A times 1 is equal to A. 0 is called the additive identity, as you know. 1 is called the multiplicative identity. And then we have the fact that A times 0 equals 0. And in fact, that is actually demonstrated because of the so-called distributive law. And everybody needs to understand that the distributive law and how it works. And so these are the basic rules of arithmetic that you want to teach the children, and that applies to these counting numbers. Now, it turns out pretty much these same rules are going to apply to all the numbers that we're going to be adding on to the counting numbers. But first, you obviously want to teach kids how to count. First, they learn to count with the place system, and then they learn to add and multiply, obviously starting with small single-digit numbers, and then they go to double digits, and then they learn these rules. And I like to make a game out of it, and I like to start kids as young as they can. I've got children and grandchildren of my own, and they start counting when they're 2, 3 years old. And then they begin to learn how to add when they're 2 or 3 years old. Just small numbers. I'm not making it formal out of it. I like to make more of a game out of it. The more mathematics can be treated as a game, the easier it is to learn and the more success you're going to have. So anyway, that's what we do with the counting numbers. Now, a little later on, and I don't mean for very young children now, but when kids are getting older, a little bit older, you start teaching them how the powers work, the powers of 10, 10, 10 squared, 10 cubed, and so on and so forth. And you start teaching them then that the 10 cubed is 1,000, and you give names to it, and 10 to the 6 is a million, and 10 to the ninth is a billion, and so on and so forth. And so you teach them things like that. And I don't think you want to introduce scientific notation to really young children. I think just teach them to count and to multiply and to add numbers, and then you're going to teach them subtraction. And now, so of course, subtraction right away presents a dilemma, because right away they find out that they cannot subtract a large number from a small number. This would be meaningless with just the counting numbers. And of course, at that point in time, and I'm not sure what the right age for this is, this will probably depend on the child, you then introduce the integers, which is nothing more than the counting numbers 0, 1, 2, 3, and then you take a mirror image of them and put labels on them and call them negative, and take them in the other direction, and these are the negative numbers, and these are called the integers. Now, one of the things that you want to do with integers, I believe, and even starting with counting numbers, is you want to draw a straight line, and you want to give them the idea that you can actually use them to measure things. And rulers are a very good way to do this, of course. And then the negative numbers would go in the opposite direction. And sometimes I like to use the idea that it's a ladder. You're climbing a ladder in a vertical way, and you go up the ladder for positive numbers, and you go down into the hole down below, if this is sea level, for the negative numbers. Now that's just, again, it's just something you can do. There's nothing magical about it, but you want to give them an idea of the sense of that. Now, one of the problems you run into, of course, then right away, when you extend this to the negative numbers, and like I said, I'm not sure at what age is best to do that. You have to use your judgment on that. It really, when your child is maybe ready for it. But when you do that, then you are faced with extending the definitions of plus and times to the negatives. Now, of course, it isn't too hard to deal with the addition, because the whole idea of the negatives is that you wanted to have 7 minus 4 is 3, and you want to have 4 minus 7 is minus 3, and that's the same as 4 added to minus 7, for example. And of course, you can set them up. If you use the number line, it's very easy to give them a geometric representation of how to add and subtract integers. Um, the problem comes in with multiplication. They've all learned the multiplication table for positive numbers. They know that 3 times 4 is 12. Now the question is, what happens when you start multiplying, say, a negative times a positive? Well, it's not too hard to motivate that that should be a negative number, and I'm not going to get into that now. You should know how to do that if you're any kind of a teacher. But then you get into negative times a negative, and of course that has to be a positive, and that's a little hard to motivate. And I might give you a talk on that someday, but or you could just take it as a definition if you need to, in order to make the rules of arithmetic consistent. But all the rules that we had before carry over for addition and multiplication, and it is essentially the same rules. The only rule you're going to add now when you go to the negative numbers is you're going to now say that for every number a, there exists a number minus a called the inverse. So when you add them, you get 0, and this is called the inverse property. And you don't have that with just the counting numbers. That's why you have the integers. Now, the other way you go, and sometimes you should do this and maybe want to do this before you introduce negative numbers, just back when you're at the positive number stage, is you've got to introduce the idea of fractions. And I'm not going to give you a lecture on that. You know how to do that, but they've got to understand what fractions are: 2/3 and 5/2 and mixed fractions, 2 and 3/4 and things like that. And they need to know how to add them and to multiply them. And now, of course, the thing that you can now do is you now can say that if you have any fraction a, there's another fraction b, so that when you multiply them, you get 1. Again, this is the inverse property, and this is called a inverse usually, or 1 over a, where a is any fraction. And these are called, by the way, as we all know, rational numbers is what mathematicians call them. And that's okay if you want to introduce that terminology. But you now have, again, all of the rules of arithmetic work, except you now have this new rule, and this is called the multiplicative inverse. Just like above you had the additive inverse up here. Now, it can be debated as to whether you should introduce fractions first or negative numbers first. Historically, mankind invented fractions first, and they only had the positive numbers and the positive fractions, and only later did they introduce 0. That took them quite a while, and then they introduced the negative numbers. Pedagogically speaking, which is best to do, I'm not myself completely sure, because I haven't taught a lot of elementary mathematics, and so I would kind of play that by ear, and I might defer to people that have had more experience at that than me. But in my view, this is the kind of thing that you want to teach people. Now, of course, what happens is shortly after you teach them about fractions, almost at the same time that you teach them about fractions, you have to introduce the concept of a decimal expansion, because you're going to have 1/4, as you very well know, is going to be 0.25, and you've got to teach them that this is 2 times 1/10 plus 5 times 1/100th, and so forth and so on. And you're going to have to teach them that, the decimal expansion of numbers. And then you now have numbers like 12.375, and they've got to understand what that means. 1 times 10 plus 2 plus 3 tenths plus 7 100ths plus 5 1,000ths and so on. And they're going to learn that some fractions have a repeating decimal that goes on forever if you let it go on. It never ends. If you divide 1 by 3 and expand that out, there's no end to it. And so at some point, you're going to truncate it and say, well, this is 0.333, and you're going to stop, and that's going to be an approximation now. And they have to understand that any number can be approximated to however much accuracy you want with a decimal expansion. Now, this calculator is, and I'm sure there's others that will do the job, is very good for this because it has a fraction key. And so you can actually teach a kid a lot about fractions using this calculator. And it can convert fractions into decimals and decimals into fractions. And I'm not going to give you a lesson on that now. We cover that really in the foundation course, because as soon as you get out of post-elementary mathematics, you'll be wanting to be able to start using this. And I think that's very important. They'll be learning, of course, then how to multiply and all the operations for fractions. multiplication and addition, and of course subtraction and division, which are kind of inverse operations. And they'll be learning that. And of course, one of the more difficult ones to teach them is the addition of fractions. That's actually harder than multiplication, as you know, because it's AB plus BC over, this is D, over BD. And that's, multiplication is even easier, as you know. It's just A over B times C over D is AC over BD. Going kind of fast here. But all the rules still hold. The rules that we had before, the associative rule, the commutative rule, they all hold. And of course, it's because we now have fractions that we have the multiplicative inverse. We didn't really need fractions to do the multiplicative inverse. We only needed the negative numbers for that. But once you have all of these numbers together, then you have what is often called the rational numbers, and the letter Q is often used by mathematicians to denote that. And these are the rational numbers, and it's all numbers of the form A over B, where A and B are integers. That means they can be positive or negative, and B is not zero. You cannot allow B to be zero. That would be an undefined number. And of course, you can't have even 0 over 0 is undefined. But in any case, you can never have B equal to 0. This would not be a defined number. And you have all the rules of arithmetic that we've already discussed. And pretty much this is what a child needs to fully understand probably by the time he's 5th or 6th grade or so and is beginning to get close to post-elementary. Now, another thing that I think is probably worth doing at this point is to be sure that as you're doing all of this, you're building up these number systems, you always want to tie this to geometry if you can with a number line. So you got 0, 1, 2, 3, 4, and -1, and -2, and -3. And this is like an infinite ruler. And then every rational number falls to a unique point. 1/2 would be here, of course, and 2/3 would be here, and -1.5 would be here, and things like that. And of course, you want to give the kids a lot of exercises to make sure they understand it. And then they also understand that there is a decimal representation or expansion for every rational number. So P over Q can always be written as some series of integers, and if you want to be abstract about it, A1 through AN, and maybe I should say A1 down to A1, AN down to A1 dot, decimal point, and then you got B1, B2, and so on out. And of course, you want to give lots of examples of that. Now, the thing about rational numbers are, and this is something that you tell kids, fairly early on, it's not too soon, is that when you expand a rational number this way, there will always then be a series of repeating decimals. And then it will repeat over and over and over. That's easy to demonstrate and to convince children of, or to prove if you feel a need to prove it. Although I don't believe you should get into very much rigor with children. I think you should just explain things to them and let them experiment and see. But for example, if you take 3 and we'll take 1/3, it'll be 0.3333. If you take 4 and take 1/3, or I take it 1 over 4, it'll be 0.25, and then it ends in zeros. So in the case of 1/3, you had 0.3, and that repeated forever. And once you identify a repetition, you put a bar over it. That means that particular cycle repeats forever. 1/4 was just 0.25, and then 0, and the zeros repeated forever. Now, 1/5 will be 0.2. Let's see, what is 1/6? 1 divided by 6 is 0.16666. Let's do 1/7. And there we get, now this is interesting. 7 finally is the first one that's kind of interesting, is 0.1428 5 7, and then it starts over. 1 4, and then they rounded off in the calculator to 3 because that's where it stopped. But this 6 numbers here repeats forever. The next 4 will be 1 2 8 5 7. The next 4 will be 1 4 2 8 5 7. If you go on, this will just keep repeating forever. And that's what 1/7 does. And any rational number will do that. It'll have some sequence of digits that then repeat and repeat and repeat. And that is one of the defining qualities of a rational number, is the fact that its decimal expansion will always repeat. And indeed, you can also show that if you have a decimal expansion that has a repeating sequence, it is a rational number. So this is really an equivalence. You'll have a repeating now set of digits in the expansion. Now, I wouldn't be telling third graders about this, or fourth graders probably, unless they were very precocious. This is something that you might want to point out to kids time in the 6th, 7th grade, something like that, or maybe even you wait till post-elementary. That's okay too. It's not a big deal. Um, and the question now is, are these all the numbers you need? Well, that's a very, very good question. And my answer to that is, if you are going to do what I call ordinary practical math, then the rational numbers are all you need. Any number that you ever do on a calculator or a computer will be a rational number. It'll be either expressed in decimal form or in fraction form. Like I said, I'm going to put 1/7 in as I want to make sure you can see this. I'm going to put 1/7 in as a fraction, and then I'm going to use the conversion and convert it to a decimal, and there it is, 0.142857143. Now this calculator has more digits in it than it displays. I don't know how many more, but somewhat more, and it certainly knows what you've done, and if I convert it back, it'll convert back to 1/7. So I can convert back and forth between its decimal expansion and its fraction, and I think that's a good thing to do with kids. You take 2/7. Let's just do 2/7. And whoops, I went too far. So let's do 2/7. Now it's in. Now let's convert to decimals. Well, there it is. 285,714 starts over again, 28. And then it converts back to 2/7. And then if I multiply that times 1/7, hit equal, I get 249ths. And of course that has some sort of, and I may not see the repetition here because it can go way out. It can go as far as that denominator is. And in fact, I do not see it here. I'd have to go further out to see it. This calculator isn't going to show it. You'd need a more powerful computer to actually see then what is the repeating decimals of that 249s. But I can tell you it would be. And it would be a chain that was no longer than 49 characters. So rational numbers are really all that you need for ordinary mathematics. In fact, whenever you take a measurement of any kind of measurement, you're going to come back with a measurement is going to be a rational number. And in fact, it's going to be a rational number, and then it's going to be plus or minus an error term. In other words, you cannot measure anything, I don't care what it is, precisely. There's always an error term of some sort. So all you need then for practical math really is rational numbers. Now, that's certainly up through what I would call the elementary foundational level. Now the question is, for students that are going to go on beyond practical math, what do they need? And this is where there is not necessarily a universal agreement beyond math that's practical. And here's what I think that they need. The first thing I believe that students need is they need to, by the time they are in their late pre-calculus math training, in our case that is in what we call Tier 4, they need to learn about complex numbers. Now this is not what is normally done today, or if it's done in a very weak and incomplete way, in my opinion. And what they do not need is they do not need rigor. For example, I don't think at this point in time it does a student any good to have any kind of a rigorous definition of irrational number. What they know at this point in time is they know about the real number line. And they probably know that the rational numbers, which are the ones they always use, have repeating expansions. And what that means is there's numbers that don't have repeating expansions, and those are called irrational. And that's all right to tell them that much. But beyond that, I don't think these are just simply not rational. And so that would mean that they would have a non-repeating expansion. And that's okay to say that, but I don't think you need to get into it any deeper than that, frankly. But what you do need to do is to teach them complex numbers. And I have a video on that that I highly recommend to you about how that should be done and why it should be done. And I like to do that in late pre-calculus. Now, when we get beyond pre-calculus into calculus, the first thing I do is, of course, I review the real number line with them, but then I introduce them to what are called infinitesimals. And I do this now in a non-rigorous heuristic way, but it is consistent with what would be a rigorous approach. For example, everything we teach people about the real number line, while we're not doing things rigorously or as deep as we could, it's correct based on our current understanding of the real number line. And I do the same thing with infinitesimals, and this is part of what is called the hyperreals. And the reason I do that, the infinitesimals are a wonderful tool to use in calculus. In fact, mathematicians have been using infinitesimals for a long, long time. Archimedes used them, Newton, Leibniz used them, Euler used them, and in fact, it wasn't until the mid-1800s when mathematicians began to try to make everything they were doing very rigorous and complete, and they could not figure out a way to include infinitesimals in their treatment, that they were banned. So in the 1800s, the mid-1800s, I'll say 1860s, they were banned from mathematics. Mathematicians said, well, we can't figure out what they mean in a rigorous way, and even though they have intuitive meaning, we just don't think that we should be using them at all. That wasn't totally unreasonable because mathematicians set about trying to prove everything that they were doing. Well, it turns out now in the 1960s, mathematicians figured out how to do it rigorously. Infinitesimals are now treated just as rigorously as other numbers, as real numbers, for example. And so now they're back in, and from a rigorous viewpoint. And it is very easy to teach people how to use them. They're very intuitively clear, and it makes teaching calculus and understanding calculus much, much easier. So I believe that should be introduced to students that are now going into calculus. So what do we have then? We have the real number system, which I believe all students need to know about, even in practical math. We add complex numbers at the advanced pre-calc level for reasons that are both pedagogical and practical. And then when we get into calculus, we add the hyperreals, again taught in a heuristic way, but consistent with the rigor that mathematicians, of course, have brought to that subject. Now, you might say, okay, when do you actually introduce rigor? Well, if you're going to have a student that is actually going to become a mathematician, a theoretical mathematician, I might add, then you begin to introduce rigor. And that's a whole nother topic that is very fascinating and interesting, and so that will be on the next video that I will discuss that, because it will take quite a discussion to discuss how is it appropriate to introduce mathematics students, people who are going to become mathematicians, into the rigorous treatment of the number systems. We'll do that on the next video, but for now what you need to know is you need the real number system at an intuitive heuristic level. Although it's accurate, you don't tell them anything that's not true, and this is for practical math, and this is very simple. You use the real number line for that, and then you need complex numbers introduced in a very similar way, heuristically and practically, and you do that in advanced pre-calc. You have to already know trigonometry before this is going to make any sense. It's very much helps you understand trigonometry. In fact, I don't think you'll fully, well, I don't think you'll understand trigonometry as deeply as you can until after you have understood complex numbers. And then you need I'll just call them hyperreals, but I'm really talking about the infinitesimal component of it when you get into calculus. And everybody needs that. I mean, this is engineers, scientists, it doesn't matter. And the reason is you can quote prove things with hyperreals and infinitesimals much easier and more clearly than you can without them. And that makes the teaching of calculus much easier. It makes the learning of calculus much easier, is what I really should say. Of course, it makes the teaching easier too. And so that's what you need. So these are the stages you need things in. And then after that, you'll go on into the more advanced theoretical treatment of the numbers, which I will talk about on the next video. Dr. Dell, see you on the next video. Bye-bye.